All right, so I guess we can get started. So I just want to remind you guys that homework number 4 is due next Tuesday. Okay, so a few days from now, you probably want to make sure you start early. So I have your exam number 1 graded. I have your grades put it online on Moodle page. You should get a notification of that, or you can check it up on Moodle for your exam grade. Okay. The distribution of the exam grades, there are 4 of you guys score greater than 90% or 90%, and 1 of you guys are in the range of 80 to 89%. There were 8 of you guys in 70 to 79%, 6 in between 60 and 69%, and 1 in the 50s, 1 less than 50. Okay, the average of the class is 72%, a little bit above 72%. All right. I know some of you guys probably didn't feel like you have done well in the exam. So make sure there's 3 more exams. There's still room to grow. Just make sure you start early. So if you just start for the test the day before, it won't work, as you know. So make sure you start as early as possible, also on the homework assignments as well. Okay. So physics is one of the science classes that it needs you to put constant efforts throughout the semester. It doesn't work if you started just like 1 day or 2 days or 3 days or maybe 5 days before the exam. That wouldn't work. Okay. All right. So let me just quickly go through the solutions with you guys. So it's up online on the Moodle page on top here. If you click on this one, it will give direct you to the solution. Okay. So for the first one here, this is about ideal gas law. So at 2 different conditions. So then basically, you can rewrite the ideal gas law PV equal to nRT. So that gives you PV over T equals to nR. All right. So then if you do PV over T, that should be equal to constant because N and R, they are both constants. So then P1 V1 over T1 should be equal to P2 V2 over T2. All right. You're looking for P2 here with the rest of parameters given. So then you solve for P2 in that sense. Number 2, this is on root mean square speed of the hydrogen gas. Okay, a lot of you guys didn't multiply the molar mass by 10 to the negative 3 to kilograms. Okay, so that's one of the common mistakes you guys made on this one. All right, but otherwise you just plug in the numbers here, square root of 3RT over M. This equation is given in the formula sheet. The T also you want to convert into Kelvin. Okay, so 2 conversions you need to pay attention to. Number 3, this is about the gas spill. So gas will expand at the same time the tank will expand a little bit. Okay, so then you'll be looking at the difference between the expansion of the gas and the tank. All right. So you will be using coefficient of volume expansions for both gas and the tank. So they are already given as volume expansion coefficient here. All right. For the temperature given, they are given in Fahrenheit. So you want to convert them in degrees Celsius. You can take the difference first and then convert the difference into Celsius. Okay. If you do that way, or you can do them individually, like convert 62 Fahrenheit to degrees Celsius and 38 to degrees Celsius and take the difference. Okay. Then you just plug in numbers over here. You'll figure out it's 0.171 gallons for spill for the gas. Number 4, this is for a calorimeter. I think we did this one example in class. You guys are also having similar example during the lab. Okay, so basically the heat for lead plus the heat for water should be equal to 0. Okay, and you're solving for T then. Okay, so that's on that one. P5, this is a purely just ideal gas law. You are looking for the moles, okay? And this is about the same you are doing in the lab, ideal gas law lab, okay? So just plug in numbers. You want to convert 65 milliliter into meters cube. Okay, that's one thing. You want to convert also, you want to convert the temperature from degrees Celsius to Fahrenheit, to Kelvin. Okay. All right. Number 6, you have a block of ice and then you are adding heat to it. So as I mentioned in class, you can just examine the process one by one. The first step is raise the temperature of ice to 0 degree Q1, and then compare that to the heat added. So Q1 is less than the total heat. So that means the ice will begin to melt. So you calculate for Q2, what's the heat needed for totally melt ice, okay? So it turns out that Q2 plus Q1 is already greater than the Q that you add totally. So that means your ice will only melt partially, okay? So then you will just stop somewhere here during the melting process. So that means your temperature is still 0 degree, okay? 7, so you have ice and water mixture this time. So then you can pick the 0 as the middle point, 0 degree in Celsius as the middle point, and then calculate how much heat loss for water it is. Okay, you can calculate that. Then you can calculate for the ice to raise to from minus 10.2 degrees Celsius to raise to 0 degrees Celsius, what heat needed as Q1. So that turns out to be less than the heat water will lose, okay? So that means ice will melt, will at least start to melt. So then again, you calculate how much heat is needed to fully melt ice, Q2, and it turns out this again, Q2 plus Q1 is already greater than the Q of water. Okay, so that tells you your ice will only partially melt again. Okay, so for this one, it's the same scenario as the previous one. Okay. Number 8, this is about the work done for isothermal process. So you'll be using this equation for work done along with the ideal gas law, PV n equal to nRT. Okay, for isothermal process, T stays the same. All right, then you can solve for your V1 initial volume in that sense. There's one example. I think there's one problem in the homework as well on this. Number 9, this is about entropy change. So entropy change of S1 of the system 1 and system 2. 1 will be the house, 2 will be the outside, outdoor. Okay, so it will be Q over T. So for house, it loses heat, so it's minus. Okay, for the outside, it receive heat, so it's positive. So it's minus 1.6 times 10 to the 8th for Q1. Q2 would be 1.6 times 10 to the 8. Okay. The temperatures, they are given in degrees Celsius, so you want to convert them into Kelvin, the SI unit. Okay, and you will get the change in entropy in that case. Number 10, this is a refrigerator. It tells you this is a Carnot refrigerator, so you'll be using the ideal coefficient of performance here between the two temperatures that are given in degrees Celsius. Again, you want to convert them into Kelvins first when you calculate this coefficient of performance. Okay, so that tells you 6.454 will be TC over TH minus TC. Okay, you can convert just TC into Kelvin for TH minus TC because it's the difference in two temperatures. So you don't necessarily have to convert those two in the denominator. Okay, if you do, it's the same. Then you are looking for the latent you're looking for the total amount of work. Okay, so then you can relate the work with coefficient of performance and then the heat lost. of the water. So the water goes from 20 degrees to -2. So that means there are three processes here. So first, water temperature drops to 0, and then it freezes, and then the ice becomes ice. The ice temperature drops further down. Okay, so Q1, Q2, Q3. You need to add those three Qs up for the QC. You'll take absolute values. So then because when you calculate QC will be, if you use this equation, QC will be negative, but you just want to know how much heat is lost, so you take absolute value. Okay, so gives you that absolute value, then you can calculate what's the work by so using this equation. So work then equal to QC over KR. Okay. All right. Questions you guys might have on the solutions? Okay, so if not, then we'll go back to the lecture here. So today we'll be still looking at chapter 18. We might get a chance to start chapter 19, but we'll see how where we'll end up with. Okay. So briefly, last time we took a look at the electric field. So this is by examining the analog to the gravitational field. Okay, so so for gravitational law, it's G capital M small m divided by R squared, similar to the Coulomb's law, F equal to K Q1 Q2 over R squared. Okay, so then they are similar in that sense. So for electric force, then we can also define an electric field. We call it E. All right. In the sense of gravitational field, we say it's G. So then force in this case will be equal to Q times E, depending on what sign you have for the charge Q. So force will be in the same direction. If Q is positive, force will be in the opposite direction to the electric field if Q is negative. Okay. So electric field it points away from a positive charge Q, okay, and then it actually points towards the negative charge Q. Okay, so that's how the direction goes. For a point charge, so then you can write electric field as E equal to KQ over R squared, all right, at your point of interest. Now, if you have multiple charges, then the electric field at a particular point of interest will be equal to summation of all the electric field from all the individual point charges. Okay. But keep in mind when you are doing the additions, the summations, you are doing vector summations. Okay, not simply scalar summations. If you have a charge under the influence of electric field, then force is equal to, for the magnitude wise, is equal to Q times E. The acceleration will be the net force divided by the mass. Okay, Newton's second law there. We also took a look on electric field lines. So these are imaginary lines, okay, to help us visualize the electric field. Okay, so for electric field lines, they point in the same direction of the field vector at every point. They start at positive charges or from infinity. If you have a region that only have negative charge, then the line starts from infinity. Okay. They end at negative charge or infinity. So if you have positive charge in the region, then it will end at infinity. Okay. Field lines are more dense where the field is stronger. Okay. And for electric field lines surrounding a positive charge, so they point from the positive charge towards infinity. For the negative charge, they point from the infinity towards the negative charge. Okay, and then the line densities will indicate the strength of the electric field as well. In this case, positive Q, negative 2Q. So this will have twice as many lines as this gap because E field is directly proportional to the magnitude of the charge Q. All right. If you have charges nearby each other, then if you have positive and negative Q, then this will be the electric field line look like. Okay, if you have positive 2Q and negative Q, then you have more lines surrounding the the larger Q, less lines surrounding the less Q. Okay. If you have two identical charges, then in the middle of these two charges, the electric field will be 0. All right. So for lab this week, you are going to do field mapping. So you are going to, you'll be mimicking like two charges, positive and negative, by connecting the electrodes to a positive and a non-negative terminal of the battery. So then that's a positive and a negative. And then you'll be drawing out the electric field lines. So the lines in blues are the electric field lines. Okay, you should get something similar to this. The green lines are equal potential lines. Okay, you might get something like this. In the lab, you are more likely to have maybe just one full circle of green lines, and then the rest will curve out like that, like parabola lines. Okay. You'll be probing the electric potentials between 2 points today. You'll get the details in the lab manual. Okay, so this is the lab we are doing this week. All right. The next section we are going to talk a little about the electric forces in biological particles. So there's a lot of electrostasis throughout our body. So for example, for the DNA strands, it's heavily negative charge molecules. Okay, so there's negative charge in there. Water makes majority of our body, so it's polarized. So it's positive near the hydrogen atoms, but it's negative near the oxygen atoms. Okay, so that makes a water molecule as a dipole, which means you have a positive charge and a negative charge inside the same molecule. Okay, it's called a dipole. So a dipole is simply you have two opposite charges Q separated by a small distance L. Okay, so that forms a dipole there. All right. So I think we just need to know that much about that section. Next, we'll be looking at the electric fields and then its interaction with conductors. Okay, so so if you remember when we introduced conductor, we said there's for material to be a conductor, then there's free electrons can be moved around. Okay, so that will cause the charge redistribution. So for example, if you have an electric field here, now you put a conductor in the middle over here. All right. Now, because there are free electrons that can move around, so in the case that electric field line will be altered, so then you'll have, if this is the electric field, so then negative will be redistributed towards the left end, right? Because the electrons are negatively charged, they will be under the influence of electric force, in this case, when they are placed in the electric field. So then the force is to the left. So then all the electrons will be redistributed towards the left, or all the free electrons. Okay, leaving the right hand side to be positively charged. Okay, so the atoms on this side will lose certain electrons, so then they are positively charged. Okay, so in that sense, then this side is negative charge, so the electric field line will end at the lowest end. Okay, and then on this end, you'll have the electric field line starting from those part over there. Okay, now inside the conductor, the electric field will be 0. Okay, because if not otherwise, then electrons will be, if the electric field is not 0 in the middle, then electrons will under the influence of the electric field. Okay, so then it will be redistributed. Okay, so in equilibrium, you should have electric field inside the conductor to be 0, right? Now on the surface of the conductor, then it's the other case. Okay. And for the electric field line on the surface here, you'll find that the lines at the point where it's in contact with the surface will be perpendicular to the surface. That means it's in the normal direction of it. Okay, so this is the case. So if not, if this is in this case, then charge will be pulled, all right, with this horizontal component of the force, electric force. So then will be redistributed. So the result will be, it's going to be perpendicular to the surface. Okay, so then it will be in equilibrium. All right. So two things on this slide: electric field will be 0 inside a conductor. Electric field lines on the surface of conductor will be perpendicular to the surface of the conductor. Okay. All right. And all the excess charge should be on the surface of the conductor. Okay. So if not, so then the charges will repel each other. Okay. So if this is a positive charge conductor, then will repel each other. Now, due to the electron conduction, electrons inside conductor can move around freely, so then charge will redistribute it. Okay, so it will be on this surface over here. Okay, so they want to stay as far as each other because they are repulsive to each other. Okay, so then the surface is the place for the electron, for the charges to be staying in that sense. Okay, so just keep in mind, for a conductor, the charges can move freely inside the body. All right. So again, the electric field will be equal to 0 inside conductor. So if you have a charge over here in the middle of the conductor, this is like this is empty over here. If you have charge here, so then you will have electric fields from here to the inner side of this conductor. But then inside the body of this, you will have no electric field. Okay, due to that the charges can move freely around, then that will alter the electric field. So E will be equal to 0 inside the body of the conductor. Then after that, you'll have the electric field going outward. Okay. So some application is electric shielding. So for example, if you have metal chute, then you are safe, insulated from electric. Okay, so you can in that case you can touch any um, charges or maybe electricity. That should be fine because you are inside the conductor, the metal chute here. So the any charges will be on the surface of the chute, and then inside the chute you'll have no electric field, so you are safe in that sense. Also, like for the airplanes, so when it's hit by lightning, the passenger inside the airplane is they are safe because they are inside the conductor. The airplane is made of metal. Okay, so in that sense. All right, so to summarize, properties of a conductor in electrostatic equilibrium. So the electric field is 0 inside the conductor. And just outside the conductor, the electric field lines are perpendicular to its surface. All right, and the excess charge will reside entirely on the surface of the conductor. Okay. All right. Now, a lot of times you'll see uniform electric field. So how is that created? Okay, so that is created by having two metal plates placed close to each other, parallel to each other. So then electric field line will point from positive charge to negative charge, positive to negative. Okay, you'll have them as the same charge. So if you have same like the positive Q on this guy, then you have negative Q. So say positive 5 coulombs on top, then you have negative 5 coulombs on the bottom. Okay, so in between the plates, most of regions, the electric field will be parallel. They will be uniform. Okay, now just on the edges, they are curved. So the electric field on the edge is not so uniform, but for the majority part of the inside the plates, you will have uniform electric field. All right. The Earth itself, it's actually charged, negatively charged. Okay, so it has a electric field about 150 newtons per coulomb. All right. So then when lightning happens, the charges goes from the cloud to the earth. Okay, so that's when it happens. For electric fields on uneven surfaces, okay, you'll have actually more charges on the more sharp edges. Okay, so for the example, on this edge, you'll have more charges there. On this more like not as sharp as this guy, more flattened area, you'll have less charge. Okay, all right. Or if you have the most curvature, you'll have the largest charges. Okay. And the application of that is a lightning rod. Okay, so for high-rise building, you usually see a lightning rod that is having sharp tip. So then charge will accumulate at the top over here. So then lightning will go through there, and then this rod will be grounded. Okay, so this charge will be distributed to the ground in that sense. Some more application of electrostatic. One is this device called Van der Graaf generator, used to generate charges, a lot of charge accumulation. So um, the the belt here, okay, so will produce charge due to the rubbing of this drum with the bell here, and then the extra charge will be going through this metal accumulate on this conductor. Okay. And then you can use that for experiment. For inkjet printers, it's also utilizing the electrostatics. So the ink, okay, comes here through a nozzle here, will be charged by this electrode and then goes through a deflection plate. All right. And then in that sense, the ink could be injected to the paper, okay, to print out. All right, so that's for chapter 18. So we'll start chapter 19 here. All right, so I'll pause for a few seconds to see if you guys have any questions about chapter 18. All right, I guess not. So then, um, so chapter 18, we'll talk about electric potential and electric field again. Okay, so remember when we talk about gravitational field, then we talk about also gravitational potential energy. Okay, so this is again the analog to that concept there. All right, so just similar to if you are doing work against the gravitational field, you build up gravitational potential energy. Similar here, if you are doing work against electric field, then the electric potential will be built up. Okay, so in this case, change in electric potential will be equal to QE times D, while for potential energy is mgd. Okay, so it's a similar fashion here. You are just replacing m with q, you are replacing g with e. Okay, so in that sense. So then the delta U will be the electric potential here in this case, okay? All right. So the work it takes to move an electric charge parallel to the field line, okay? So in that case would be minus QED, all right? So you are going again in that fashion to move it from here to there. So then delta U equal to minus W equals to QED in that sense, okay? So electric potential V then is defined as change in electric potential divided by the divided by the Q 0, right? In this case, so it will have a SI unit of volts, which means joules per coulomb, right? So delta U is the electric potential equals to Q times delta V. So then for electric potential is equal to Q times V. or simply just or Q naught times V, or simply just Q times V. Okay, if you have a test charge of Q0, then it's Q0 times V. If you have general just a charge Q, then it's just Q times V. All right. So let me just go back one slide here. So for electric potential, it's in the units of volts. Okay. If you multiply Q by delta V, then it gives you energy. Okay, so Coulomb times volts equals to joules of energy. Also, it's often used energy for electron, 1 electron volt, that's a unit of energy if you are dealing with electrostatic. So then 1 electron volt is equal to E is the Q times V will be the potential in volts. Okay, so that's about 1.6 times 10 to the negative 19 in joules. Okay, so if you see 1 electron volts, then it's a small number of 1.6 times 10 to the negative 19 joules. All right, so let's see how is the electric potential related to electric field. Okay, so we'll start with the simple case that if you have a uniform electric field generated by these two plates over here, so the change in electric potential, then it's equal to work done over Q. Okay, so if you go from point A to B, then force is equal to F times D, or force is equal to F, distance D. So that gives you work equal to F times D over Q. All right. Now F is equal to Q times E for electric force. So then this is QED over Q. Okay. So then change in electric potential is equal to electric field times the distance. Okay. Linear relationship. So V from point A to B is equal to E times D. All right. Or in the other way around, you can write E as a function of electric potential divided by the distance. All right. Let's take a look this example here. It says I guess not many of you guys have seen this monitor, but this is a very old-fashioned computer monitor. It accelerates electrons and then directs them to the screen in order to create the image. Okay, that's how it works. So it says if the accelerating plates are separated by 0.59 or 953 centimeter apart, and have a potential difference of 22,500 volts. What's the magnitude of uniform electric field between this? Okay, so it tells you basically V from A to B as this guy, and then distance as this. What will be the electric field? All right, you guys can give it a try. We can take a look at this solution in 2 minutes, I think. All right, so let's take a look. So on this one, I'm looking for electric field. So then it tells you the potential and then the separation. So simply you'll be doing V over D or delta V over D. Okay, so it tells you delta V is 22,500 volts, then divided by 0.953, but that's in centimeter. Okay, so again, you want to convert that into meters. So that will give you 2.36 times 10 to the 6 volts. Okay, so it's very high voltage inside the TV. So or in general, like screen monitors, there's high electric field there. So you will see like the signs on the back, it will say caution high voltage inside when you open it. Okay. Um, so any questions you guys might have? I saw one response have the right number, but with the not the number with not with the right order or magnitude. So probably less conversion issue they didn't do. All right. So if you are clear, we'll then move on. So similar to when we talk about, if you take a look on the figure here on the right, similar to for a gravitational field. So when you start with a high point over here, the ball will roll down and then roll up over here, and then reaches the zero velocity and then comes back and forth, back and forth. Okay. So what happens here is you have conversion of potential energy to kinetic energy, and from kinetic energy back to potential energy, and back and forth, back and forth. So in that case, the energy is conserved. Mechanical energy is conserved because gravitational force is a conservative force. Okay, similar to gravitational field, electric field is also the force, electric force produced by electric field is also a conservative force. Okay, so if you go from one point, if this is a electric field, you have a region that has electric field. If you go from one point to another point, okay, then you are simply converting, if the only force on the object is the electric field, okay, so then you are just converting between electric potential energy to the kinetic energy, okay, so then back and forth in that sense, okay, given that the only force is the electric force. So electric force is also a conservative force. Okay, so up to this point now, we know there are three forces. They are conservative force, the gravitational force, the electric force that we just learned, and then also the spring force by a spring. Okay, that what we learned last semester. All right. So in general, if you just have a conservative force, then mechanical, the kinetic energy and potential energy will be conserved. That means at point A, you'll have kinetic energy 1/2 mVA squared plus the potential energy at that point. So this potential energy can be can include both the electric potential energy and the gravitational potential energy. All right, if you have gravitational field that is present. That should be equal to 1/2 mVB, the kinetic energy plus the potential energy at point B. Okay, so at point A, the two energies should add up to be equal to the two energy add up at another location. Okay, so for simply, if you just have electric potential energy, then U is equal to Q times V. Okay, so U stands for potential energy, Q is the charge, times V is the electric potential at that point. Okay. So you can rewrite that kinetic energy at point B should be equal to kinetic energy at point A plus potential energy minus potential energy at point B. And UA will be QVA, UB will be QVB. So then this is equal to Q times VA minus VB. All right. All right. So so because there's a sign consideration here, you want to pay attention to other than for gravitational force for the mass, it's always positive. But in here, you have Q could be positive and could be minus. So let's take look at the sign here. So if you have positive charge, if your Q is positive, if the positive charge accelerate in the direction of the so it will oscillate in the direction of decreasing electric potential, okay? Because force then will be in the direction of electric field, then that will increase the kinetic energy. So then electric potential energy will decrease, okay? So positive charge will oscillate in the direction of decreasing electric potential line. On the other hand, negative charge will oscillate in the direction of increasing electric potential, okay? All right, but for the potential energy, then you multiply potential by Q. So in both cases, the charge will move to a region of lower potential energy, okay? Just keep that in mind. If the only force is the electric force. All right, so we'll take a look on this example here. This one says if you have a proton has an initial speed of 5.5 times 10 to the fifth meters per second, what potential difference is required to bring the proton to rest? Okay, and it's asking you what potential difference is required to reduce the initial speed of proton by a factor of 2. What potential difference is required to reduce the initial kinetic energy of proton by a factor of 2? All right, so 3 questions here. So again, I'll give you guys a few minutes to work on this, then we can take a look on the solution together. All right. So let's take a look here together. So this one says a proton. Okay, so this proton. Um, it actually implies a couple piece of information here. So for proton, the charge is 1.6 times 10 to the negative 19 coulombs, positive, right? Because electron is negative, proton is positive in that sense. Um, then the mass of it is also given by the fact it's a proton. So for proton, this is 1.673 times 10 to the minus 27, okay, kilogram. So the word proton implies those two pieces of information there. Now it says it has initial speed of, so let me see, this initial is at point A, speed of 5.5 times 10 to the fifth meters per second. So let's say it goes from point A to point B, all right, in that sense. It's asking what potential difference is required to bring the proton to rest. So that means VB will be equal to 0, right? That's about bringing it to rest. So we should just write small v in this case because that's for speed. So there's different signs here. Capital V stands for electric potential, okay? Small v stands for speed. All right, so let's take a look here. Or let's use a different sign here. So let's use U as speed, okay? So I'm going to just use U as speed, UA, small u and small ub here, just in for that consideration. So 1/2 MUB square should be equal to 1/2 MUA square, the speed square, plus Q V, capital V minus VB. Okay, so that stands for electric potential. And this is the speed. All right, this is according to energy conservation. You should have conservation of mechanical energy, which means kinetic energy plus potential energy should be equal to 0. Okay, you get this equation from the previous slide. So it says UB is equal to 0. So then this guy is 0 for pi A. Okay, so this is 0. So then you're looking for actually, let's do it this way. So UA minus UB, let's say this is the potential difference, delta, okay, V from B to A, all right? So then this should be 0 equals to 1/2 the mass, okay, 1.673 times 10 to the minus 27 kilogram times 5.5 times 10 to the fifth meters per second square, okay? And this is delta of V B to A, right? Or from A to B. So then you put B in the first place, A to the second place. But if you can flip the subscripts A to B, then it becomes negative. Okay, so negative of Q 1.6 times 10 to the negative 19 times this guy. Okay, so you can figure out that delta of V from A to B should be equal to 1/2 of 1.67 times 10 to the minus 27, 5.5 times 10 to the fifth meters per second square divided by 1.6 times 10 to the negative 19 coulombs. Okay, I have everything in SI unit, so my final answer will be in SI unit. Okay, so this will give you 1.58 times 10 to the third V. Okay, so about 1,500 volts there on this guy. All right. For B and C, it will be similar to A, but it tells you different speed, right? For B, it says what potential is needed to bring the proton speed by a factor of 2. So that means 1/2 of times the mass times a factor of 2. So reduced by a factor 2, that means 1/2 of initial speed square, right? So equals to 1/2 MUA square plus Q of VA minus VB in the case. Okay, you can rearrange the terms. You can move this guy to the other side. So then it's 0 times. So this square will give you 1/4 UA square, right? So that equals to 1/2 MUA square minus 1/4 times 1/2 M still UA square. Okay, and then plus the same thing, Q or minus Q V from A to B in that sense. So you can solve for this because this guy now becomes 3/4 times 1/2 MUA square, right? So compared to, sorry, that's not in the window there. Compared to this guy, this is 1/2. This is 3/4 of that. Okay, so you don't have to repeat calculation by just looking at the factor. This is 1/2. This is 3/4 of 1/2. Okay, so just treat this as kinetic energy at A, and then this is kinetic energy at A. Okay, 3/quarters of kinetic energy at A. So that will tell you your final your potential that you are looking for. The potential difference should be 3/4 of what you get in part A. Okay, so in that sense, you don't have to plug in all your numbers there again, but this will give you 1.19 times 10 to the third. Okay, for part B. For part C, you are doing it similarly. So it says bring the kinetic energy to half. So that means 1/2 of 1/2 initial kinetic energy, okay, equals to the initial kinetic energy plus Q of VA minus VB, okay. Again, move this guy to the other side. So 0 equals to 1/2 of initial kinetic energy square minus Q of VA to B, okay. So this is 1/2 of the initial kinetic energy. So then your VAB should be 1/2 of the initial 1.5A times 10 to the third, okay, which give you 7.9 times 10 to the second volts on this, okay. All right, questions you guys might have? All right, if you guys are clear with this, then we'll stop here. Okay, so the lab will meet as scheduled, and then on Friday our lecture is still all online. Okay, see you guys.